Have you ever looked up at the sky at night and wondered where all those stars come from? Well, our textbooks tell us that we figured out how stars form a long, long time ago. All stars, our textbooks tell us, form in dense clouds of gas, which collapse under their own gravity and heat up until nuclear fusion kicks in and a star is born. Simple, right? Well, it turns out there is no theory of star formation that takes all the properties of a cloud and predicts in detail how quickly stars will form or which kinds of stars will form. Now, the lab experimentalist would love to go up to a cloud and take a look at the temperature, the magnetic fields in those clouds, and the turbulent motions in those clouds, and play around with those factors. They would like to put a flame under a cloud and heat it up, or apply a giant magnet up to it, or grab it and shake it and see what happens to isolate those effects and quantify their contributions. Now, of course, we can't do that in astronomy. They're too far away. But we don't have to. Nature has done this for us. Behind me is a beautiful close-up image of the center of our galaxy, the Milky Way. At the very center is a supermassive black hole, 4 million times as massive as our Sun. And orbiting this region is a ring of strange star-forming clouds. There are hints that these clouds are hotter than clouds found elsewhere, that they are pervaded by stronger magnetic fields, and that their turbulent velocities are unusually powerful. These are exactly the experiments we need to improve our understanding of star formation, once we figure out exactly which experiments nature has performed for us. For instance, these clouds are being continually blasted by streams of energetic electrons. These particles smash into atoms in the gas and boot out even more electrons. This cascade of collisions heats the cloud at a known rate, and thus allows us to pin down the unique temperature of this system, which is key to understanding the impact of temperature on star formation. In addition to this, the gas in this region is tortured and twisted by strong gravitational fields, a consequence of being so close to the galactic center. This culminates in a spectacular array of vortices and violent shock waves. By studying how these shock waves squeeze and energize the gas as they ripple through the clouds, I've developed observational features that allows us to test just how turbulence affects star formation. Now, my work so far has been purely theoretical, and so the next steps of my thesis are to search for these predicted signatures in real data. And by combining observations and theory in this extreme laboratory, I'll be able to test star formation theories in a whole new way. Thank you.